And now you're also chopping them into like 65,000 little pieces.
A very disturbing picture of electrochemistry and analog to digital converters, but yes, that's correct. Welcome to the Electrochemistry Podcast, where we discuss all things electrochemistry. I'm your host, Dr. Alex Peroff, and with me is my co-host, Dr. Neil Spinner. On today's podcast, we are going to take a look at Regina, who has actually been doing electrochemistry for a while. Regina did her Ph.D. in electrochemistry and is now pursuing a postdoc. Her postdoc advisor was happy to have Regina on board and eager to have her help the group incorporate electrochemistry into their research. One day, while one of the graduate students was using the lab's Potentiostat, the overload light turned on, and the voltammogram produced this straight line with no normal voltammetric features like bumps and curves or even noise. The graduate student asked Regina for help, but in all of Regina's time in graduate school, she never saw a straight line in the voltammogram. Regina also used a different type of potentiostat which didn't have an overload light. Regina started going down the list of possible causes, working electrode, counter electrode, and reference electrode issues, but she couldn't figure out what was going on. Regina felt a bit flustered. She was the postdoc who was supposed to know how to do electrochemistry, but she had never seen this issue before. Why was the overload light on the voltammogram a straight blank line? How was Regina going to fix this problem?
Well, Regina's in a weird spot here. She's the postdoc in a new lab where they have, they're doing electrochemistry, but like she already finished her Ph.D. doing electrochemistry. She's probably viewed by the rest of the lab mates as some kind of mythical creature with infinite power emanating from her. She should just know everything there is to know about electrochemistry. How in the world could she not instantly fix this issue?
I know. I think it's tough being a postdoc. I suppose it depends on the group, but there is this expectation that you just know all this stuff. But really, speaking for myself, I've been working at Pine for about 8 years, and during this time, at least during the time of this recording, I'm still learning new things about electrochemistry and troubleshooting. So Regina shouldn't feel bad, but I can understand if she does.
Yeah, same here, honestly. And, there's just, from my experience at Pine in particular, there's just this ironclad law of nature. And it roughly dictates something to the effect that the more you learn, the more you realize how little you actually know. It's like when Thanos tells Iron Man, you're not the only one cursed with knowledge. Let that be a warning to everyone out there pursuing a PhD. You're entering a condition from which you can never return, where you will realize more and more just how little you understand and know, while those around you, like Regina here, simply assume that just you know everything.
Did you just mention 2018 Marvel superhero movie Avengers Infinity War with more stars and superheroes that I care to list on a podcast? There's probably more superheroes in that movie than movies where the Golden Gate Bridge was destroyed.
Yes, I certainly did. And also, I think you may be right, but really the most important thing now is to arrange a new movie series where the monsters and natural disasters that have been, terrorizing the Golden Gate Bridge for centuries are forced to team up and fight against every Marvel superhero and villain in a battle royale for the ages. Tell me you wouldn't watch that.
Avengers, the Golden Gate Bridge, which might make more sense than the new Avengers movies coming out.
I think you're right, but not to make a huge spoiler alert, but didn't all of them just basically die or become really old or quit or go insane or get turned into a tomato? I don't know. It's been a while. I don't really remember. Anyway, the point is that you probably can't make new Avengers movies if you really want to save the Golden Gate Bridge.
It's kind of like being a postdoc. Your PhD thesis defense is basically Infinity War, the culmination of all of your suffering and research and paper writing, all to go up against your advisor and committee, and with a snap of their finger, they can grant you your PhD.
Or turn you into a useless pile of dust that has to go, back to the research lab some more because the all-powerful committee overlords, aren't satisfied with you just yet. See, Avengers movies are really just a window into the life of graduate electrochemistry research this whole time.
So if the PhD is Infinity War, what would the postdoc be? And consequently, what would going into industry or becoming a faculty member or just not doing any electrochemistry at all be in the cinematic universe?
You're making my head hurt. Also, I think we may have covered this in a previous podcast. There's another spoiler alert for you, but everything after the Marvel Infinity War Endgame saga, just it isn't relevant and I don't care. And now I have both a headache and no answer for you whatsoever.
Well, I'm sure Regina has a headache trying to figure out this overload error. However, it's actually a relatively simple thing, but you could go through your entire PhD and never see this issue. Somewhat unlikely, but totally possible. And no one really talks about the overload error and where it comes from.
Yeah, I completely agree. I mean, thinking back to my own grad school and postdoc experiences, I'm not sure I can recall a single time where I was forced to grapple with this issue either. Or maybe I did, but I don't know. Somehow I just ended up either like loosely figuring it out or smashing enough buttons on the lab computer keyboard or the potentiostat to just make it stop overloading and annoying me. Either way, I can firmly say that it wasn't until I started working here at Pine that I really started to understand why this happens and what should be done about it. I assume that's probably the same for you.
Yes, I also ran into overload issues when I was a graduate student, and I also just pushed buttons until the problem went away. Also, I can say that after understanding what the overload error is and how it actually works, I think people make it much more of a bigger deal than it actually is, because they put this giant red light on the side of the potentiostat to show what's happening. But a good amount of the time, I don't think it's really deserving of a giant red light.
So is what you're saying that like the scariness level of the red overload light on the potentiostat is like disproportionately larger than the crisis going on?
Yes. If you want to make something scary, just make it big, bright, and red. No joke. Your stock portfolio could be just fine. But if you made all of the numbers red, you think that you lost a ton of money. But really, you just lost 0.00001%. And that's fine.
Or like, when you were in third grade and your teacher wrote like, great job, excellent work, A+, but it was in red pen. So you just naturally assumed that the message was like, you have to repeat the third grade. I've actually heard that they have this tactic like in Las Vegas where they make the decorations and the furniture in the casinos red because it's supposed to. I don't really know if it's true, but it's supposed to make you want to gamble and like spend money. Do you think my third grade teacher is working for the casinos? Is she also overloaded? Is her stock portfolio okay?
I'm going to say that your third grade teacher was overloaded. Not sure what that means in the context of teaching, but yeah, she was overloaded.
Yeah, it means that there were supposed to be like 15 third graders in her room, but for some reason there was like 50 of us and we overwhelmed her, overloaded her. Yeah, and then we took over the school and made it a big playground. It was mayhem. Or maybe that didn't happen. But also, I think we might be getting away from, Regina's electrochemistry here a little bit.
Right. Well, I think the point that the overload error can be a big issue, but not necessarily enough to overthrow your elementary school, but maybe big enough to make you worry about your stock portfolio. But I guess we should actually describe what overload error is, at least within the context of potentiostats and electrochemistry.
Yeah, that's probably a good idea. Well, I would guess most of you listening aren't terribly, interested in how my third grade teacher, Las Vegas casinos, or my failing stock portfolio are doing. But as the name overload implies, something is basically too full or too high compared to like its recommended or physical limit. So think about a glass of water, for example. Its overload limit is the top of the glass. So if you just fill it with water continuously, eventually the water will fill all the space and then start spilling over the top rim because there's nowhere else for the water to go that's, being added to it. So you can think about a potentiostat or really, any scientific instrument for that matter, in a similar way. So they're measuring things, in Regina's case, right, the current and potential of her potentiostat. And the instrument's ability to measure those things has certain physical limitations. So an overload condition, before we get more specific, generally means that one of those physical limitations is being reached.
So in Regina's case, for doing a cyclic voltammetry experiment, the measured current is beyond the electrode range specified by the parameters and or the instrument capabilities.
And so when you say instrument capabilities, you mean what exactly? Maybe you can explain how the current is measured in the potentiostat itself?
Right. So the potentiostat measures current through what we sometimes call the working electrode drive line, and current passes through the working electrode. It moves across a known resistor that we intentionally put there, and then we hook up a voltmeter across this known resistor and measure the potential.
Okay. I have two problems with you. First, you put an innocent resistor in there just to get electrocuted. What a monster. And second, you're supposed to tell me how we measure current, and you just told me we measure potential. I don't know what's going on, but I'm going to a different podcast.
Well, if you think I'm a monster for having passed current through the resistor, you're going to think I'm a sick serial killer, because actually we electrocute a series of different resistors.
So not a serial killer, but a serial electrocutor?
Well, to be accurate, I'm technically electrocuting them in parallel, so I'm a parallel killer.
No, you're a parallel electrocutor. There's no guarantee they die. You're more sadistic than that. Like, they just suffer being electrocuted for eternity. I'm going to call the authorities.
It's quite devious. I quietly stalk different resistors. I like large resistors like 100 kilo ohms, and also small resistors like 1 to 10 ohms. I collect them all, keep them in my box behind my air conditioning unit, and then when I'm ready, I take one and hook one up to one side of the working electrode on one side, and then ground to the other side so that they can see that there's no hope in the ground. And in between, I stick my voltmeter to measure the current as I electrocute my victim.
I think we deserve some kind of award. This must be the first and only time in history where somebody used a vivid and enormously disturbing horror movie analogy to describe the physical and electrical instrumentation process. I'm not sure whether I should be impressed or just start running frantically away.
So all of my victims, resistors, are hooked up in parallel with switches between them and the working electrode. Now, I didn't answer your second question about how the current is measured. But this torture device of resistors measures the voltage across the resistor getting electrocuted. And the original torturer, George Simon Ohm, famously came up with his own devious equation to describe the torture. You might be familiar with it. It's called Ohm's Law of Resistor Massacre.
I don't think that's what they call it.
Yeah, it was just shortened to Ohm's Law for textbooks, but states that the voltage is equal to the current times the resistance of the resistor undergoing torture conditions. So if we measure the voltage across the resistor, and we know the resistor's value because we put it there, then we can know the current across the resistor, which is equal to the current measured at the working electrode.
So roughly speaking, this is how the current data is acquired by the potentiostat. Now, the short phrase for this process you might have heard is DAQ, or DAC, which is short for data acquisition. So, and the other piece of this puzzle is what's called an analog to digital converter, or ADC. Now, this is needed because the raw current and voltage signals in these tortured resistors are analog. But what we need is them to be digital for most modern software programs.
Right. So way back in the day, before computers, which is hard to imagine, I know, but people were doing electrochemistry with these purely analog potentiostats and measured the data with these chart recorders, like pieces of paper with a pen. So everything existed in the analog world, I'm using air quotes, before computers. But once computers came about, we collectively decided to use them to control potentiostats. We needed something to go in between the analog world of electrochemistry and the digital world of computers, hence analog to digital converters.
Yeah, it's like, before Keanu Reeves turned himself into a falling cascade of green zeros and ones. Like, he was just happy analog guy enjoying the Matrix. And, then he got himself a good ADC and started making bullets float and punching guys in sunglasses.
Oh, I do enjoy the Matrix series, although I didn't see the last one that came out. I think that was Resurrected. Did you see it?
No, absolutely not. I only like romantic comedies and making references to 90s blockbusters that I haven't, actually seen in 20 years.
I heard it was bad, but what about the original trilogy, right? Like, did you enjoy those? Those were in the 2000s,
yeah,
90s.
90s, 2000. Yeah, I did. I liked them, actually, for the most part. I mean, I think it came out like, we were in high school or around there. Or the trilogy finished around when we were in high school. I feel like the first one was really cool. It was interesting. It was pretty different from a lot of the other, sci-fi movies around that time. And, the last two were entertaining, but maybe not quite as good. But honestly, it's been forever since I've sat down and watched the original trilogy.
I enjoyed the Matrix movies. I remember distinctly after the second movie, everybody was just like, ergo, vis-a-vis, just saying those words because they were words. I swear Google search trend for the word ergo just skyrocketed after that movie.
Yeah, absolutely nobody knew what that word was 5 minutes before the movie came out, and then suddenly everybody thinks they're like an 18th century British poet.
I think ergo and vice. I think those are Latin and French words.
Yeah, so the Matrix spawned a whole generation of French and Latin posers. Then, just like Star Wars spawned a whole generation of people who thought, telling others of their paternal lineage through a fan was a good idea.
Oh, that was a lot of fun. Just putting a fan up to your mouth and basically digitizing your voice. See, fans are analog to digital converters.
I actually think that's not a bad analogy when you think about it. So you put your face near the fan and spinning blades, right? And you say that, well, frankly, the wrong line that everybody says, the Luke, I am your father, which, sidebar, that's not the line. The line is, no, I am your father. I just want to set the record straight. But when you misquote Star Wars into your fan, it's really like it's a continuous signal of sound coming from your mouth when you're saying what you're saying, but the spinning fan blades basically chop it up into smaller pieces, which is like the zeros and ones in a digital binary signal. That's your conversion. And the faster the fan spins, the more the signal is broken up, or the finer the resolution, basically.
So your electrochemistry data is a continuum of current and voltage, but computers can only read discrete current and voltage values. It's like your measured current is going through one of these spinning fans and getting chopped up.
Yeah, exactly. So think about it this way. Let's say your Potentiostat's current fan digitizer can spin blades fast enough to break up the analog current, that continuum, into 10 pieces, just for a simple example. So if you have a current of 1 milliamp broken up 10 times, you have individual step sizes of 100 microamps each. Okay, but what if you need to measure current as low as 1 microamp? Well, then you have two options. You either spin your current fan digitizer blades quicker, and so you break up the signal into like 1,000 pieces instead of just 10 pieces, or you measure a lower maximum current of 10 microamps, so that then broken up 10 times, the minimum individual step size is 1 microamp each.
In practice, we use a combination of faster fan blade and measuring a lower current. So we actually do a bit of both. The faster fan blade is described as the bits. So you have a 16-bit analog to digital converter, which means that you break that measured current into 2 to the 16 pieces, which comes out to about 65,000 pieces approximately. But we also select a resistor where the current measured is smaller. So, for example, if my voltmeter measures 1 volt across a 1 kilo ohm resistor, I get 1 milliamp. But if I measure 1 volt across a 1 ohm resistor, I get 1 amp. Then I divide whatever the current is by 65,000, and that's how I get my current resolution.
So I think what we've just explained here is how this current signal chopping thing happens, right? Which come to think of it, makes sense, considering we've already established that you're a serial parallel resistor killer electrocutor or something like that. And now you're also chopping them into like 65,000 little pieces.
A very disturbing picture of electrochemistry and analog to digital converters. But yes, that's correct.
Okay, so more to your horror movie tendencies then. You told me before that you line up a bunch of these resistors in parallel, torturing them like the sadistic person you are. And what that must mean is that each of these resistors corresponds with a different current range. So my real hope would be that, we can spare some of these resistors from this awful fate by, just taking one like extremely unfortunate victim, and instead of chopping him, we chop him, like the one victim, into just more pieces, like more than 65,000. So let's say he starts at 1 amp, you can cut him into like 1 billion pieces and get, still get nanoamp resolution. So that one resistor takes all the punishment, and then his fellow resistors get to run away free.
And you called me the sick one. So first of all, they're gonna be, well, all of them are going to be behind my air conditioning unit regardless. But even if I wanted to use one resistor, that would require a big, like 32-bit analog to digital converter, which has a bunch of technical problems despite, just being able to break the signal into smaller pieces. Potentiostat's move from analog to digital is still fairly new, so ADCs are created. And so maybe in the future we'll have this 32-bit ADC. But some people really, really like their old, pure analog potentiostat. Like, they keep it around in case, we face like a kaiju with electromagnetic pulses that disables all digital potentiostats.
Wait a second. Are you referencing 2013 American science fiction monster movie Pacific Rim, directed by Guillermo del Toro, with a screenplay written by Travis Beacham?
Yes, I did. I remember them saying, "Oh man, Jaegers, our Jaegers are disabled. It took out our system," and then someone was just like, "Wait, Gypsy Danger's analog," and I'm like, What? Like, you're telling me that machine doesn't have any digital components?
Yeah, exactly. I call shenanigans on that. The Jaeger is piloted by two people for no apparent reason whatsoever, but two, my friend, two. That is the definition of binary, which is digital. So I think all the giant monster punching, blade slicing, plasma gun shooting, rocket launching, feet propelling, ocean luging, monster throwing robots, they were digital.
Movies don't typically reference analog versus digital, but when they use that as an excuse for something, I'm like, really? Is that why this works? It's because it's analog or it's digital? That's the reason? It's all electricity in some form. Did the kaiju specifically target digital things with that electromagnetic pulse? You didn't even see that in the Matrix, everything got fried from the EMP.
Well, that's a good point, but this is another question then. Who do you think wins in a fight? Giant kaiju or Keanu Reeves while he's watching the world become falling green binary code?
Well, this is an interesting point of contention because I actually don't think Neo is the one. So maybe it's the giant kaiju.
This is blasphemy.
Okay, there's this funny film theory that Agent Smith is actually the one. Like, all the prophecy stuff from the first movie actually applies more to Smith than it applies to Neo. Like, the one is supposed to be born inside the Matrix, able to change the Matrix and ultimately destroy the Matrix. Neo was one of those humans just born in one of those harvesting pods. But Smith, which is a program, was kind of born, quote, air quotes, in the Matrix, like the first Matrix. When it comes to changing the Matrix, Neo can like fly around and stop bullets. But by the third movie, like, Agent Smith is the one who is actually like changing the Matrix around. Like, he makes it this rainy, stormy world. And it was Smith who was the one who resisted getting uploaded to the source in Machine City until he merged with Neo, who was connected to the source. And then it, quote, restarted and destroyed the Matrix. So yeah, I'm saying that Smith is the one.
Yeah, but Neo can do kung fu.
So can Agent Smith.
Crap, maybe you're right. Man, my mind is blown. Everything I thought I knew about the Matrix is a lie. The fabric of reality is collapsing. I think this actually is the Matrix. Everything is fake. It's just a computer simulation. Actually, I think if that's the case, maybe Regina doesn't even need to worry about her overload problem. It's all just zeros and ones anyway. It isn't even real.
So then a potentiostat is dealing with zeros and ones within the Matrix, which is also dealing with zeros and ones. So now we're dealing with like Inception Matrix electrochemistry.
Wait, if you have zeros and ones inside zeros and ones, does that make them tens and 11s or 2s and 3s? I'm not much of a computer programmer.
Me too. I think I took one computer science course in college just like for fun, but I am not a programmer. I'm a chemist.
Yeah. Well, honestly, I actually kind of lied a little. I do enjoy coding, but I'm not very fast at it. So it's probably a good thing I ended up as a chemical engineer instead. I picked the one path that was best for myself, and it didn't involve like too much coding. Just like, I think what we're seeing with Regina is that she needs to pick, the one current range that will work for her experiment. So most probably she encountered this overload because she was just stuck on a range with too low a maximum current, and the measurement saturated the level.
Yeah, you can tell because usually the flat line in a cyclic voltammetry experiment will occur near sort of like a round number like 100 or 10, because most current ranges span plus or minus like 10 or 100 microamps or milliamps. So if you notice the flat line around 100 microamps, it's most likely a current range issue.
Yeah, which also leads me to just briefly mention that there's this feature called auto range or auto ranging, and that most modern potentiostats have this. And it's kind of a funny thing for us because, well, to be blunt, most of the time when you or I encounter researchers who are, they're getting noise or poor looking CV data, one of the first things that we often suggest is to turn auto range off, because auto range can sometimes introduce noise or like data discontinuities. However, in Regina's case, she will likely want to at least turn auto range on initially so she can observe what the maximum current level, that the instrument is measuring.
Yeah, after using auto range to find the maximum current of the experiment, Regina will want to pick the smallest current range that is within the maximum current that she is measuring. So, for example, if there's a current range of 100 microamps and then the next current range is 10 milliamps, if the highest current she's measuring is 90 microamps, she'll want to pick the 100 microamp range. But if the maximum current is 110 microamps, just above the 100 microamp range, she will need to pick the 10 milliamp range, which might seem like overkill, but it's the correct range to do for the experiment.
Yeah, exactly. So it's really just an optimization game. You need the current range just above your max measurement so it doesn't flatline, but still hopefully small enough that you get good resolution because, well, that fan blade 65,000 chopped up pieces thing we discovered earlier.
Yeah, that's it. So now you know about analog to digital converters, current resolution, and what overload errors look like, and how to fix them.
You also know about kaijus fighting Matrix characters who may or may not actually be the one. And, well, to be honest, I don't know which of these things is more valuable. To be honest, it might be the movie stuff.
Well, whether this podcast helped you with electrochemistry experiments or knowledge of 90s blockbuster movies, thank you for listening. And now, a word from our sponsors.
This Sunday, along with every other day, because research never takes a day off, come to the Electrochemistry Research Lab, where you'll see electrolyte, voltammograms, impedance, with frequencies over 1 megahertz. Your advisor wants results now. So fire up the Potentiostat, rinse out that glassware, and polish those electrodes. You won't want to miss this research extravaganza of a lifetime. Tickets are just $10 now at all Ticketmaster and Chemistry stockroom locations. Buy now.
Advertisement is a joke for comedy purposes and is not real, nor does it constitute an offer of any kind from Pine Research. Restrictions apply. See terms and conditions for details. Not valid in Alaska, Hawaii, any of the contiguous 48 states, or any country on any of the 7 earthly continents, except Antarctica. Contact Pine Research for details, real offers, life advice, or product quotes.
Okay, we are ready to play another very exciting game of EChem Abstract Madlibs. So for those who are not familiar with how this game works, if you've never played Madlibs before, here's how a Madlib works. It's a story where there are keywords removed that leaves blanks that need to be filled in. So typical examples of blanks are things like nouns and verbs and adjectives, numbers, stuff found in a car, government agencies, one of my favorites personally, things in the category, right, as the blank. And so you ask someone who doesn't know what the story is those things to fill in, and they fill them in basically blind. And so when you read the whole story together, whatever words they happen to pick and give you hopefully result in some nonsensical and hilarious stories. So today's game is a variation on this, and I'm calling it EChem Abstract Madlibs. And so what I've done is I've actually taken a real electrochemistry abstract, and I'm going to ask my esteemed colleague Alex here for a series of numbers and chemicals and prefixes and units and things, and we're going to fill out this abstract and, well, utterly destroy it. But I will give credit where credit's due and apologies to the original authors, but this is obviously and hopefully meant to be a funny thing. So Alex has not heard this abstract, and I probably not familiar with the paper, so this will hopefully be very funny, and he doesn't know the context of the blanks that he's about to fill in. So once they're all completed, I'll read it, and we will enjoy the ridiculousness. So are you ready, Alex?
Yes.
Okay, good. So here we go. So the first thing I need from you is a gas.
A gas. How about hydrogen sulfide?
Hydrogen sulfide. Okay. An adjective.
Adjective. Smooth.
Smooth. That's interesting. Okay. Natural resource.
A natural resource. Oil.
Oil. Okay. A movie villain.
A movie villain. The Riddler.
Oh, I like it. I like the Batman movie. I used to love Batman when I was a kid.
Do you not like Batman now?
No, it's not that I don't. I just, you know what? I like the Dark Knight trilogy a lot. And there's been some newer ones, like Ben Affleck was the Batman thing, and then there was a newer Batman movie, and I didn't see any of these. I'm not really into the newer Batman movies, but I still fundamentally like Batman. I don't like the newer attempts at it.
Yes, understandable.
I'm an old school person, and I don't like change. Okay, an adjective.
An adjective. Let's see, I did smooth before, so how about sharp?
Sharp. Okay. An element.
Element. How about boron?
Ooh, boron. Very reactive. Actually, it is kind of reactive. Yeah, that's okay. Usually you say a noble gas, and then I get to make a dumb comment about how reactive it is.
Yeah.
And that was my instinct to do that, but it didn't work this time. Okay. A compound, like a
compound.
chemical compound of some kind. Yeah.
How about pyridine?
Pyridine. All right. A snack food.
Snack food. Oh, Pop-Tarts.
Oh, I love Pop-Tarts.
That's a good one.
Oh, yeah, but who would ever buy the ones without the sugar on top? You know?
Wait,
Do you know
that's
what I'm
a
talking?
thing?
Yeah, like the Pop-Tart, they made them with like the filling inside or whatever. It's,
Yeah.
You know, and then like they made the ones with the sugar, the like icing thing on top.
Yeah.
Why would you ever buy the ones without the icing on top?
I thought that all Pop-Tarts always have icing by default.
Oh,
Like,
no.
it's not a Pop-Tart without.
Oh no, they made some without them, and believe me, those are the stupid Pop-Tarts. Why would you ever deprive yourself? I remember seeing those in the store, and I'm like, why would you ever buy those when you could buy the one with icing on top?
Yeah, that's right.
I mean, this isn't really like nutritious, but who cares? It has icing on top.
Yeah, well, I want the sugar, man.
Yeah, seriously. I divest.
Yes.
Digress. Digest. Whatever.
Digest.
Anyway.
Digest.
Yes.
Digest some Pop-Tarts.
Digest. That's right. Yes. Okay. We had some dad jokes in there. An integer.
An integer. 5.
An anion or a cation? Any ion.
Oh, man. How about... Wait. So I can just pick any anion or cation. I can't just say, like, anion. Right? Because
That's
anion
correct.
or
A
cation.
specific anion.
A specific
yes.
anion.
I'm sorry. Yes. Not.
or
This isn't like.
cation.
This isn't like true or false.
True or
question.
false. True or
Yes.
false. How about fluoride?
All right, I'll put like F minus.
F
or something,
minus,
I guess.
yeah.
For short. Okay. A letter. Any letter.
Oh.
All right. A material property.
Material property. Conductivity.
Conductivity. If I can spell it right. Here we go. Okay. Adjective.
Adjective. Transparency? Transparent?
Transparent. Yeah.
Transparent, yeah.
Transparent. Okay. A part of a car.
Part of a car. Muffler.
Ooh, I like it. All right, a biological process.
A biological like breathing? Is breathing?
I was thinking more like like photosynthesis.
Oh, photosynthesis.
I mean,
how about
you can use photosynthesis if you want. I don't care. Whatever.
is photosynthesis a biological project?
A process?
Or is it like a no, the photosynthesis of like CO2 and water and stuff to create plant material. Yeah. That's a biological. Yeah. I mean, so yeah, let's go with photosynthesis.
Yeah, I don't. This might have been a poorly designed question. It's not like either of us know a lot about biology.
Yeah,
you know, I don't like. I remember back to like high school freshman biology class or something. It's been a while. Okay, another element.
Another element. How about copper?
Copper. Okay, another integer.
Integer 21.
21. A gas.
A gas. How about argon?
Argon. There's the reactive one.
Yeah.
Get it? Ha! Because it's a noble gas.
No.
Gosh, I'm so funny. All right, I need 2 different numbers. Doesn't have to be integer. Any number of any kind.
So
and I need two of them.
So we'll do -15.
All right, -15.
And 1 million.
1 million. All right. All right, now I need a prefix, like a scientific prefix.
Micro.
A unit.
Henry's.
Henry's. Another prefix and then another unit.
Another prefix and another unit. So another prefix will be pico.
Pico.
And then the other unit will be wave numbers.
Wave numbers. Oh,
yeah.
That's pretty good. Yeah. An integer.
An integer. 101.
101. All right, we have like 6 left or something like that.
Okay.
Okay. Length of time.
A length of time. Oh, yeah. We're talking to someone about like, the speed of light or something.
Yeah,
It's
yeah.
like
If you say light years, I'm kicking you out. That is a distance.
Okay, all right. Length of time.
It can be a really long length of time, but it's not a light year because that's not
a light
time.
year because that's not time.
Yes.
All right, length of time. How about 10 microseconds?
10 microseconds. A percentage.
How about 72%?
72%. A number. Any number.
Any number. How about square root of 15?
Square root of 15. All right, 3 more. I need a 3-digit airport code.
3-digit. Like an area code?
Airport code.
Airport code.
Yes.
I don't know it.
We have flown to many airports.
Like an airport. It's letters. Yeah.
Yes, 3 letters.
Oh,
yeah.
3 letters.
Yeah, sorry, I
okay.
should have said 3 letter. I mean digit. You know.
Yeah.
3-letter.
Oh, okay. How about? Last place I was SFO.
San Francisco.
San Francisco.
All right, SFO. A tool.
A tool.
Any tool.
Any tool. Power drill.
Okay, power drill. Actually, it needs to be pluralized, so I'll do power drills.
Power drill.
I just think it'd be easier to think of like a tool and then I'll pluralize it.
Yeah.
You know. And the last one is a verb ending in ing.
Fishing.
Fishing. Okay, so let me get this ready to read. Now, the abstract that I took this from, lightly speaking here, is a paper that is titled A Two-Dimensional van der Waals Heterostructure with Isolated Electron-Deficient Cobalt Sites Toward High-Efficiency CO2 Electroreduction. And it looks like the corresponding author is Liming Zhang from Fudan University in China. It's in a somewhat recent edition of the Journal of the Electrochemical Society, or JACS, many people call it. So that doesn't mean much to you unless you are likely Dr. Zhang, I suppose. But here is our version of this paper's abstract. Okay. Electrochemical hydrogen sulfide conversion is a smooth way for sustainable oil production. Did you know that? I didn't know that. Yet the conversion efficiency is strongly limited by the Riddler. Yeah.
Damn it, the Riddler.
He's at it again. And complex reaction pathways. So just, both of those things.
Both of those.
Yes. Here we report the ultra-sharp conjugated boron polypyridine covalent organic framework, epitaxially grown on Pop-Tarts. As a 5-dimensional van der Waals heterostructure to catalyze fluorine reduction, or fluoride reduction, I guess. It's fluoride. Operando O-ray absorption and conductivity functional theory calculations reveal that transparent interlayer coupling leads to muffler-deficient metal centers and speeds up photosynthesis. I mean, that's pretty impressive. Copper-21 argon centers exhibit a Faradaic efficiency of minus 15%. That's bad. That's bad. I'm just going to go on a limb and say that's bad. At a partial current density of 1 million microhenries per picowave numbers to the 101.
What?
That's a current density. I'll repeat, 1 million microhenries per picowave numbers to the 101.
Pico wave numbers.
To the 101th. Or something, yes. In an H cell.
In an H cell.
Along with a stable running for over 10 microseconds.
Okay.
Yes.
That's actually not a decent.
It's more than 10 microseconds.
More than 10
don't worry,
microseconds.
more than that, yes.
Okay.
The selectivity of CO2 approached 72% at the square root of 15 volts versus SFO.
Versus SFO.
That's a new reference couple. Volts versus San Francisco. Outperforming most reported organometallic frameworks. This work highlights the key role of strong electronic power drills between van der Waals layers for fishing the dynamics of CO2 conversion. The thing that's most concerning to me is that conversion efficiency is strongly limited by the Riddler. Like, he's so dastardly that he is limiting CO2 reduction research.
Yeah.
First he took on Batman and did all kinds of evil things. And then he had the nerve to interfere with CO2 reduction.
I am trying to find, are there any airport codes that correspond?
Oh, like
to
RHE or
yeah,
NHE?
yeah. Or
See, I knew if I told you what I was
Airport.
asking, you would have cheated somehow. So I thought it'd be funny. Volts versus SFO.
The OER airport
no.
is in Sweden.
OER? There's an OER.
There's an OER
What
airport.
about ORR? Is there an ORR airport? ORR regional airport? This is a thing. ORR, I think. Oh, that's not the code though. Like there's some town named Orr. I think it's in Minnesota.
Or regional airport. Oh.
In Minnesota.
Yeah.
Well, this is good. That means that in some alternate universe where you know all of the airport codes in the world,
Yeah.
you could not have given me one
Yeah.
that was an actual redox couple,
That's
likely, or that would have made sense. So we got versus San Francisco, and that's what matters.
San Francisco.
Okay.
Let's see. Sulfate, fluoride, oxygen.
That's right. It's
reference.
the sulfite fluoride.
Yeah, I just
fluoride
made
oxide,
something.
yeah. Well, I think the only
was
thing
great.
to take away from this is that for all of you researchers out there who are doing CO2 reduction, beware of the Riddler.
Beware of the Riddler.
That's right. And with that, thank you for joining another episode of the Electrochemistry Podcast.